Welcome to the Searching, Sorting, Insertion and Graphing Algorithms content for Year 13 and Year 12. We're going to start with the linear search. This involves going through each element in an array one by one. In this example, if we're looking for A, we start at element 0 and then work slowly through each element, comparing it as we go until we find a match. In this case, it returns a value of 4. A linear search works with any list, but it takes n comparisons. Try to demonstrate this linear search. Binary search is a bit nicer and splits the work up each time. It only works on lists in order. We find a rough midpoint and we see that the number is less than it, so ignore that left-hand side. And we continue repeating this process of finding the midpoint and deciding which side we don't want. It's a divide and conquer algorithm, so that means that we're splitting up the data each time. Try a binary search with the following data. A bubble sort is one of the easiest but slowest to execute algorithms. We compare each number with the one next to it and swap them if they're in the wrong order. In this case, E and A are, and we swap them. We continue comparing the numbers and swapping them if they're in the wrong order, so smaller ones on the left, bigger ones on the right, until we get to the end of the array. Then we need to go through the array once more and do the same thing. And we continue to go through the array, swapping elements when they're out of order, until we've done one complete pass through the array where we've made no changes. In this case, I'm just going to stop here because there are no more changes to be made. But in reality, that would do at least one more pass through of the entire data. Insertion sort's a little bit nicer because what we're doing is actually putting data into places. So if we assume that the left-hand side is sorted, and an element of 0 is automatically sorted, we start adding the elements from the right-hand side one at a time into the correct place. Now, what we're not showing you here is that the algorithm that makes a decision about where that element goes on the left-hand side. So there is a bit of complexity here that's been hidden away. In the exam, you'd only have to show what you're seeing on the screen at the moment. It is computationally complex and logically complex, but is much faster than the previous sorts. A merge sort now uses two pieces of data to combine them together. Starting in this case where we have two ordered lists, we compare the first two elements and bring down the first element into a new list. We continue doing this with what's left, always putting the new element on the right-hand side until we have a final ordered list. This is a reasonably straightforward algorithm to think about, but again, is a bit of a divide and conquer algorithm. So we're pulling data out and working on what's left. This isn't massively evident here, but in the next example where we use an unordered list, it'll be more obvious what we're doing. There we have a sorted list. But what if they aren't already sorted? We can still use this type of sort to divide and conquer the data. Our first job is to split the data up into its individual elements. We then pair them up and merge sort them. So you can see in this example, G and H have changed order. We then take the pairs of what's left and start merge sorting, as in the original example, what's here. Now we can do this because in the first step, where we paired them up, we sorted each array. And now we're just doing merge sorts on sorted data, as we would anyway. So as you can see here, this leaves us with the left-hand side now being one sorted array, and we'll focus on the right-hand side where we do a merge sort on these two arrays here. And then finally, we're left with two already sorted arrays, and we can merge sort these like in the original example, comparing the first values and moving to a second list the values that are earlier in the list. In this example, we reach a point where one of the lists has already been sorted, and all we're left with is the second list. In this case, we can just bring all the values down. Again, a divide and conquer algorithm because it uses recursion to sort its problems out. It says, okay, merge sort these, then merge sort these. A quick sort is a different type of search, and what we're doing is picking a pivot point each time and dividing the data up on the left and the right. Please note that we don't make any effort to sort these sublists. So C is less, it's going on the left, A is less, it's going on the left, E is greater, it's going on the right, and please note that these two sublists are not in any way sorted. Once the pivot point has been done, that's in the right place, and we lock that into place. We've now got two sublists to work on, and we do the same thing. Picking C as a pivot point, A is less, and B is less. They both get put there. And with the second set, F as the pivot point, E is less, H is greater, G is greater. We can now lock these pivot points in place, and we have some small lists to carry on with. Doing the same thing again for A and B, we could select A as the pivot point, and then B goes in afterwards. We can do the same thing with E. It's a set of 1, so it's the pivot point and it doesn't need to move. And the final one, take H as the pivot point, bring that down, and G goes in front of it. Lock the pivot points, and we're left with two sets of 1. These can be both the pivot point, and there's no movement, so they both get locked into place. And then finally, we have a set of data that is sorted. This is a relatively quick algorithm, that's the name, quick sort, to make sure that data sets get sorted quickly. However, it does use recursion, so it can run into problems with memory overflows. To get rid of this, we can do a quick sort in place, and we're using two different pointers, the left and the right. In this case, I'm going to talk about them as the green and the orange. We compare them, and if they need to swap, they swap. Otherwise, the green pointer moves in one. Do these need to swap? They do, so we swap them around. We always ever move the green one. Do these need to swap? No change. Move the green one again. Do these need to swap? They do, so we swap the values. We keep moving the green pointer and deciding whether we need to swap them until the two pointers meet. At the point where the two pointers meet, the orange pointer locks into position because that is correct. Then we can do the same thing using two pointers with both sublists. So in this case, A and B don't need to move. Green moves 1, C and B need to move, and the orange pointer locks into place. Do the same with the right sublist. E and F are fine, move it 1, G and F swap, move the green one in, F and H are fine, so we lock the orange pointer. Then we've got a series of lists of 1. These can automatically be locked if they're a size 1 because they're already sorted. Finally, we've got H and G to compare. They're the pointers, so they need to swap, they do. We lock the orange one, we've got 1 left, we can lock that automatically. This is how we do a quick sort without having to use recursion.